In this section, we're going to discuss memory in C. Now, kind of a big note here, right, is that one of the points of C is that C allows direct manipulation of memory and kind of the addresses of where things are being stored. This is a little different than Java, since in Java, basically, a piece of data is bound to a name, right? We know variables as symbols, and they kind of all exist in isolation from one another. In C, things are going to be a little bit different. We're actually going to spend quite a bit of time talking about memory in C, both in this section and in many of the sections, right, many of the units to come. In C, it'll end up happening that we need to do a lot of the memory management ourselves. Or maybe I should say we'll have a lot of flexibility on how we manage memory exactly. So inside of an operating system, right, there is some mechanism whereby memory can be requested, right? And typically, right, in Java, we just kind of assume things work out. In C, we'll kind of have a little bit more control. So there are three kind of general types of memory that your program has access to: static memory, stack memory, and heap memory. Static memory is some, think of it as being some variable that's going to exist over time, right? It's going to persist while your program is running. It's actually a little bit more specific than that, and we'll go into that later. Then we have stack type of memory. Stack is basically, imagine you're calling functions, right? And every time you call a function, this function needs this variable, has this parameter. You need to have some space for it, right? So you have this so-called call stack, right? If you recall back from when you took computer architecture. Another type of memory, okay? Last type here we're talking about is heap, right? So heap is dynamic memory allocation, right? So sometimes your program is running, maybe you need to read in some data from the user, you're not sure how much data that's going to be. Well, you need to dynamically go to the operating system and request that you need this much memory, right? And you get back some address that's basically a safe place for you to store things. Now, we are going to go back and kind of talk about all three of these in detail, but for now, just kind of remember kind of the overall differences. Now, for all these three types of memory, they all have some sort of physical representation, shall we say, right? Whether I'm asking for static memory, heap memory, or stack memory, right? Anything I ask for will have an address somewhere. So if you look on the right-hand side, I kind of have a mini diagram, if you would. And the point here, right, is that these here on the left side, these are all addresses, right? So there's something being stored at address 0, 1, 2, 3, 4, 5, and all the way up, right, until, whatever is the largest number that can be stored into an integer, right? Integers basically are going to represent addresses for us, right? Addresses where different things are going to be stored, right? Because if I want to use system memory, right, I can't just say, oh, I have a variable name, right, and then go to the memory and look up that variable name, right? I can't do that, right? Every variable in my program needs to be bound to some actual physical address. Now, this is important for us because that physical representation means that data is related to other data. So, for example, right, that number 5 at address 1, well, that piece of data is right next to the piece of data for the number 4 in hex, right? These two things are adjacent, right? Rather than just thinking that, oh, I have a variable that stores this and a variable stores that, I need to think that, oh, I have a variable that stores 5, and right next to it is another piece of data, right? And this is kind of a different idea than Java, where we just say, oh, we have symbols associated with values. C supports what is called byte addressing. Basically what it's saying is we have the ability to address the individual bytes of memory rather than words, right? Words typically are based on your CPU architecture, might be some size, for example, 32 bits. But in C, we can basically just go and grab a specific byte of data, right? Specific 8 bits of information. This is going to be useful to us because basically it gives us the maximum kind of flexibility, right, to go and look up data anywhere in memory. So let's take a look at this example program. And I'm not gonna run it right now because I have the output in the slides. So this is kind of the interesting bit here, right? This is the main part of our program. What this program is doing is going to create some variables. It's going to look up kind of where they're being stored. I'm going to do a little bit of manipulation of that, and then display kind of the values that come out. So let me walk through this line by line, and then we'll take a look at the output. This is going to be basically a demo to show, okay, hey, this is the kind of power we have, right, when we're allowed to do byte level addressing, when we're allowed to talk about how variables are related in terms of where they're being stored in memory. So in the first line here, we have N1 and N2 being defined, and both of these are just variables, right, just storing stuff into them, so pretty normal. Next line, it looks, well, it's going to look different, right? There's a bunch of special characters here. We introduced the ampersand in the last section, but just as a reminder, the ampersand is saying what is the address of something, right? So n1 is a variable. It's a variable that stores a value 4. But since that value has to exist somewhere, well, then there must be an address, right? A physical address, some number that says, okay, this is where that 4 exists. And that ampersand, when you write something like ampersand n1, is going to be converted, right, from a variable called n1 to the address of where n1 is stored, right, to the address of where that number 4 is being stored. So that's what our ampersand symbol is doing. It's getting us the address of these things. Now that star symbol is saying, well, it's going to be type information here, right? Type information is something like int, right? So above we said, oh, we have int n1 to say that I'm creating a variable of type int. Well, when I write something like int star pn1, what I'm saying is pn1 is a pointer type. I could really just write that star over by the int. It might be a little bit clearer that it's type information. But the point is that that variable at pn1, that variable is not just a normal variable. It's still going to be, what it's going to be instead is it's going to be a variable that stores an address of where an int is located. So this is kind of important to understand, right? Is that we have two types of variables. One is a type of variable that contains something directly. The other is a type of variable, a so-called pointer variable, that has the address of where I could go and store or read something else. Now, I'm going to create two of these, right? pn1 and pn2, and both those special types of variables I'm going to store in the addresses of n1 and n2. Okay, next two lines do things similar, but they do it in terms of char, right? So I create two char variables, c1, c2, and then I create two char pointer variables, which contain the addresses of c1 and c2. So I've created these four variables. Now I'm going to go and print some stuff. So first thing I'm going to do is I'm going to print n1. I'm going to print its address, right? Where is that number 4 stored? And then what is the value at that address, right? So this over here on my right-hand side where I have pn1, this is saying the integer I'm going to display over here, right? This is going to be the address, right? The number where pn1 is, well, the number where n1 is stored in memory, right? Where is it stored? That number is what's being stored in pn1. So we should get some large value. And then over here, right, I have, let me mark this in real quick. Over on the right to this, right, we have this second integer being displayed, and we have pn1, well, star pn1. This star over here is actually a different star than the one over, up top here with the declarations. These are actually different things. We'll talk about the difference later. But basically what is happening is that this whole section here is saying, okay, you have a variable called pn1, which contains the address of an integer. Go to that address and look up what's there. Right, the star there means a dereference. It means I have an address, go look at what's there. So then that number 4, that's what should show up, right? We have an address, let's go and look at what's there. Oh, it's the 4 that's there. It would be equivalent for us simply to write this as n1 over here, right? So I could maybe get rid of this stuff here, right, and just write n1, and that would also show me the number 4. But when we go star pn1, we're saying, okay, pn1 is a pointer type. Take a look at the address it knows about. Look at the data there. Oh, it's a 4. And that will be displayed. Okay, so there's a bunch of different lines here, right, that all are doing basically the same thing, right? They're going to look at the different variables, right, print out the addresses, print out what's being stored at the addresses. The next line we have that's kind of interesting is this pn1 equal pn1 plus 1. So we're doing arithmetic here, but we're doing what's called pointer arithmetic, or arithmetic on addresses, right? So pn1 is not the number 4, right? It's the address where that 4 is being stored. And so when we write pn1 equal pn1 plus 1, we're actually updating the address, right? So whatever address pn1 originally stored for that 4, that'll be forgotten. It'll be replaced by the address after it, right? So we should see the address change, and we should see the value change as well, right, when we look at the output. So that occurs over here, and it also occurs over here, right? For the character, we do the same thing. We go to that variable that contains the address of that C1, and we increase it by 1, right? We move it forward by 1. And then afterwards, right, we kind of print out the updated values of C1 and C2, right? Same thing here, right? We print out the updated values after we move that pointer forward. So let's go ahead and take a look at the values that are actually displayed when we run this program. So here's our program again, and we're now looking at the output here. The output is on Windows. It's on a 32-bit system. So first thing we have, right, is this kind of initial line here. And you can see, right, we have n1 address, and you can see it's displaying some large value, right? So someplace in memory where that integer is being stored. And you can see when we looked it up, right, we got back to number 4, right? So we had the address and number 4. So that looked good. Okay, So let's see here. What happens in our program as we try to follow how the execution goes? Well, the next thing we do, right, is we say, okay, we're going to update that pointer address by 1. We're going to move it forward by 1. So we execute this line here, right? Nothing is getting displayed. It's just being updated. And then we display, right, N1 again. So notice over here in our picture, right, this is the line now it's going to be generated. Our address has changed, right? It's moved up by 4. It's moved up by 4 bytes, right? The reason for that is that integers, right? Integers are 32 bytes, 32 bits, right? So we move up by 4 bytes, right? We need to, basically what we're saying is when we do that +1, go look at the next integer in memory, right? So it's going to move up a whole 4 bytes, right? It's not going to move just 1, it's going to move up 4 because we're dealing with an integer. So we're basically looking at what is the next number in sequence, right, in the physical memory after the one I just looked at. And then over here I have my value. You notice I have some kind of dummy value there. Well, that should make sense, right? I've moved forward. I'm now looking at memory that doesn't belong to me, right? I don't know what's there, right? Somebody else has a memory allocation. I have no knowledge of what could be there. So I just looked inside and I found out, okay, this is what basically the piece of memory next to me contains, right? So it could be anything. And this, right, is really powerful, right? So all of a sudden, we have the potential to arbitrarily access anything in memory, right? We can look up addresses for anything and then do some manipulation and get somewhere else. So reading down, we get some expected stuff, right? N1, N2, C2, right? These things are kind of going to work as we expect, right? Where they're going to show some address, show some value, right? So we can see there, right? Initially C1, right, has at this address, contains the letter A, right? Remember that A is the ASCII mapping of 65. Well, I mean, don't remember it. I mean, kind of assume it, right? I haven't memorized the ASCII values, and I would suggest you don't. So I'm just kind of guessing there. No, actually 65 is right. It's definitely right. Anyways, going down, right, let's take a look at another pointer manipulation line, P1 equal P1 plus 1, right? So now we're doing the increment again on char. And notice here in our output, the address is changing by 1, right? Because now we're dealing with a char. And a char only takes up 1 byte, so we're just moving to the next char. Next char is located 1 byte from where we started, right? Not 4 away like it was for the integer. And then C again, we have some random stuff being displayed, right? So that's a special ASCII character there, right? So whatever memory was there, that's what happened to display. So overall here, the point is we have the ability, right, to look up addresses of variables and perform math in them, right, to do all sorts of things, right? We will end up getting kind of a level of indirection that's useful, right? Basically, we have variables and know about other variables. And then we also have the power, right, to go in memory and kind of change whatever we want.